Chapter 1, Introduction. Many methods and techniques of deep learning have been known for a long time. However, it is only recently that deep learning became a field of its own. At its core, deep learning is a collection of models, algorithms, and techniques such that when assembled together, efficient, automated detection and decision-making can take place. Trained deep learning models are able to detect, classify, translate, create, and take part in systems that execute simple human-like tasks and beyond. The basic building block of deep learning is the artificial neural network, or neural network for short. Deep learning is all about defining, training, and using such objects, often with multiple layers, hence the term deep. While most of this book is about the mathematical engineering of deep learning, this introductory chapter takes a more general viewpoint. It aims to introduce the field and the terminology in broad terms. In section 1.1, we introduce deep learning by discussing the general nature of the field and key terms involved. We continue in section 1.2, where we overview some of the most popular tasks and their associated deep learning architectures. These architectures then reappear in detail in the remainder of the book. In section 1.3, we discuss key ingredients of the field. It is here where we briefly touch on connections between deep learning and neuroscience, discuss computation power, and discuss the availability of large data sets. In the remainder of the book, since our focus is on mathematical formulation, these topics are seldom considered, yet we consider them here for completeness. In section 1.4, we introduce common openly available data sets that are often used to train deep learning models, both in practice and industrially. In section 1.5, we introduce the concept mathematical engineering of deep learning, which is behind the title of this book. We close with section 1.6, where we introduce common mathematical notation used in this book. Section 1.1, the age of deep learning. Classically, computers can be programmed to do complicated repetitive tasks very well. This includes automating calculations, sorting and filtering data, finding shortest paths between two locations on a map, and even executing extremely complicated weather simulations. For many of these tasks, one may consider specialized, well-defined algorithms whose specification is detailed by a sequence of steps, including logical expression, evaluation, conditional statements, iteration, and similar constructs. With such a classical algorithmic approach, software can carry out computational tasks in a faster and more accurate manner than any living creature. No human can sort a large list of numbers faster than a computer, and no dog or other non-human animal can be expected to reliably sort numbers at all. However, humans and other animals are able to think. This is something that computers still cannot do. On a more elementary level, many living beings can quickly learn to determine types of objects based on their appearance, sound, feel, or smell in a manner that up to recently was not possible by a machine. The key here is recently. The second decade of the 21st century has witnessed incredible advances in the ability of computers to carry out simple human-like tasks. These include interpretation of images, voice and text, and even learning how to execute smart decision-making in uncertain environments, such as playing games like Go. The main vehicle for this success is deep learning. The general computational area dealing with algorithms for classification, prediction, and decision-making based on data is generally called machine learning. It has been around since the late 1950s, together with the general phrase of artificial intelligence. Machine learning often involves programmed statistical techniques for tuning parameters of algorithms based on data, so that later, when used on unseen data, the algorithms hopefully work well. There are dozens, if not hundreds, of well-developed machine learning techniques and models. One class of models involves artificial neural networks, which have recently also become known as deep learning. Up to about 2010, deep learning models were generally perceived as just another class of machine learning models, which, while being interesting, in many cases were not the most successful or insightful tools to use. However, together with the advent of large collected datasets and the availability of GPUs, graphical processing units, deep learning has emerged as the norm in the machine learning world rather than the exception. There are now tens of thousands of companies around the world that are deploying and developing automated applications that use deep learning technology. Indeed, the emergence of deep learning has brought artificial intelligence and machine learning to the forefront of technology, and it is by now an integral part of almost any application. Many human-like tasks, which include image processing, voice analysis, as well as dealing with general complex datasets, are handled exceptionally well by deep learning techniques. The world of machine learning, ML, artificial intelligence, AI, and deep learning, DL, is often characterized via multiple competing terms. In addition to ML, AI, and DL, which are often used interchangeably, other key terms include data science and statistics. Related terms that have somewhat stepped out of the spotlight include statistical learning, data mining, and big data, sometimes big data analytics. When considered in isolation, each of these terms may be broadly defined with a slightly different meaning. However, when considered together, there are significant intersections between the fields and meanings of the terms. One general way to describe the key terms is to say that DL is a suite of very popular ML techniques which power much of today's AI. Further, DL is one of the key components in the toolbox of data science and complements more traditional, as well as new and novel, methods from statistics. We generally do not use the ML, AI, and DL acronyms further in the book, but rather use the general term deep learning to describe almost all of the methods and activities in the field. A first dive into deep learning. A deep learning model is a very versatile function, f sub theta of x, where the input x is typically high dimensional, and the parameter theta is high dimensional as well. The function returns an output, y, namely y equals f theta of x, where y is typically of significantly lower dimension than both theta and x, typically, but not always. Given large data sets comprised of many x inputs matching desired outputs y, it is often possible to find a good parameter values theta, such that f theta, the function f theta, approximately satisfies the desired relationship between x and y. The process of finding such theta is called training or learning. Once trained, the model f theta can be applied to unseen input data, x, with the hope of making good predictions, classifications, or decisions. Depending on the application, the input data x can be in the form of an image, text, a sound waveform, tabular heterogeneous data, or some other variant. The output data y can be the probability of a label indicating the meaning / content of the image, a numerical value, or an object of similar form to x, such as translated text, in the case that x is text, a mask image in case x is an image, or similar. In this field, one very popular source of data is the ImageNet database, which has been used for the development and benchmarking of many deep learning models. The database has nearly 15 million color images. In many models, a subset of about 1.5 million images are used for training, where the basic form of Y is given by a label, which is one of 1,000 categories indicating the content of an image. More on ImageNet is in section 1.4, where we outline other popular datasets as well. To get a feel for a deep learning model, f theta, the function f theta, consider the VGG19 model, which is one of several popular, now classical deep learning models for images. For this model, X is a 224 by 224 color image. It is thus comprised of 3 by 224 by 224, which is 150,528 values, with every coordinate of X representing the intensity of a specific pixel color, red, green, or blue. The output Y is a 1,000-dimensional vector, where each coordinate of the vector corresponds to a different type of object. Example, car, banana, etc. The numerical value of the coordinate y sub I, where say I is the index which matches banana, is a model's prediction of the probability that the input X is a picture of a banana. Ideally, when fed with an input image X of a banana, the output Y equals f theta of X will have y sub I as a high probability value, example 0.85, for the index I equaling banana, while the other y sub j for j other than the index matching banana will be low. This then allows to use f theta to classify bananas and other objects by choosing the label banana, car, etc., with the highest output probability y sub I. Such a machine learning task is called classification. At around the year 2014, when VGG19 was introduced, it was fed about 1.5 million ImageNet images X, each with a corresponding label, example banana, which is essentially a desired output Y. The process of training VGG19 then involved finding good parameters theta so that when the model is presented with a new unseen image X, it predicts the label of the image well. Note that in VGG19, theta has a huge number of parameters, 144 million. So to recap, there were about 1.5 times 10 to the 6, that's 1.5 million input data samples, each of size about 1.5 10 to the 5, 150,000 pixel values. Hence, the training data size has about 2.25 times 10 to the 11 values or numbers. This data was then used to learn about 1.44 times 10 to the 8 parameters. This is a lot of data and a lot of trained parameters. But the resulting trained VGG19 model, which we denote here as f sub theta, works well. Footnote 1. Sorry. Note that we only chose the VGG19 model here as an illustration. More efficient modern models are discussed later in the book, with image models discussed specifically in chapter 6. At the time, when the specific model was introduced, it took days to train and much longer to fine-tune. Today, such a model may take around 8 hours to train on current state-of-the-art hardware and software. Further, it can take about a fifth of a second to make a prediction with this model, that is to evaluate f theta of X. This is not an insignificant duration and can be improved upon by other models. As a matter of illustration, Figure 1.1 presents code that uses a VGG19 model, which was previously trained on ImageNet. This training of VGG19 from scratch on ImageNet is not something one would typically do in practice. Instead, we use the pre-trained VGG19 model parameters and adapt them based on another data set called Fruits 360, which has nearly 100,000 images of fruits, most of which were taken with repetitions by rotating a simple fruit of each type and taking pictures at different angles. Here we use the fast.ai library with the Python language, which also uses PyTorch under the hood. However, we could have presented alternatives with other languages, example, Julia or R, as well as other deep learning libraries, such as, for example, Keras, which uses TensorFlow. Indeed, there are many books dealing with deep learning libraries and code, with notable ones mentioned in the notes and references at the end of the chapter. This current book is not about using such libraries and the practicalities of deep learning. It's rather about the concept of key ideas. In figure 1.1a, so here's figure 1.1a. Here's figure 1.1a. Let it refresh. We present setup code, including downloading Fruits 360 from Kaggle. See also section 1.4, where we discuss publicly available datasets. In B, we present a few Fruits 360 images and their labels. So in A, there is actually very easy to use code from FastAI that downloads Fruits 360. And in B, you see a few labels, you see an apricot, a few fruits and their labels. Okay, that's in B. Let's continue. In C, there's the actual code and output needed for training, in this called fine-tuning of the pre-trained VGG19 models. This is called models.vgg19_bn, using FastAI's fine-tune method. This takes about 10 minutes to execute. This practice is called transfer learning, a concept discussed in the remainder of the book, discussed later. That's in C. Okay, so this here is easy to use, learn, fine-tune, and that does that. In D, we present an example banana image not related to the Fruits 360 dataset. Finally, in E, we execute the model prediction using FastAI's learn.predict method, where the probability associated with banana ladyfinger is highest among all possible fruits. It is highlighted in index 17. This code takes less than a fraction of a second to execute. Important to note that figure 1.1 is the first and last example in this book that includes computer code. So here is E, where you see the list of probabilities, and out of these probabilities, the probability with the index associated with banana is higher than anything else, or that probability is higher than the other probabilities. Beyond classification. Deep learning models can be used to perform various forms of tasks. The classification task described above is one type of these tasks and is often considered the most basic and illustrative task. Other tasks include regression, where y is a numerical value associated with x, which needs to be predicted. Chapter 2 presents an introduction to regression and classification tasks in the context of general machine learning, together with an overview of other aspects of machine learning. There are many more involved tasks as well. One example in the context of image data is localization, where the goal is to determine the location of an object within an image. This task can also be handled by a variant of VGG19, where the input data is still a 3 by 224 by 224 image, but the output data Y encodes the location of the object, of an object, in the image, as well as possibly the type of the object. Such a model is no longer f theta above, but some other function, say f tilde theta tilde. While the models differ, one of the useful things about deep learning is that the parameters for the classification task theta and the parameters for the localization task theta tilde are often similar, and the bulk of the training effort can be used to learn both theta and theta tilde. See Chapter 6 for discussion of a localization task, and Chapter 8 and beyond for best practice techniques for training theta and theta tilde together, namely transfer learning and composability of deep learning models. In the context of images, other tasks include semantic segmentation, where all individual pixels of the input image X are marked as belonging to specific categories or classes. In such a case, Y is of similar form to X, since it includes an indication of the class of each individual pixel. This case also clearly requires training data where each individual input pixel is considered. See, for example, figure 1.2a. So let's look at figure 1.2a. This is figure 1.2a for image segmentation. Further, one may wish to identify multiple objects in an image, as in figure 1.2b. There are other tasks as well when considering text, video, sound, or tabular data, and these are discussed in section 1.2 and throughout the book. Let's just look at figure 1.2b. So figure 1.2b, taken from this paper, You Only Look Once, okay, is about object detection and localization. So these are different tasks associated with vision. Deep learning, where is it applied? If you're reading this book, then you probably already know that deep learning is applied in many diverse contexts. By around 2020, many automated systems that involve sensing of noisy data already use some variant of deep learning. Further, many statistical modeling arenas are also starting to make use of deep learning. A medical doctor's decision can be viewed as y equals f theta of x. Here, x may be the full medical history of the patient, or more specifically, it may be the pixel information of the medical imaging, of medical imaging. In this context, y may simply be an indication of benign versus malignant, or may involve more complicated outputs such as rest for 1 week and then get checked up again. On much smaller timescales, the steering wheel actions of a driver are also of the form y equals f theta of x. Here, x can be based on the fusion of multiple sensory data of a car, and y is a steering command. Similarly, a farm worker that decides which tomatoes to pick today and which to wait on also repeatedly uses a relationship of the form y equals f theta of x. The same goes for automated voice recognition systems, for determination of the importance of text messages, for comprehending handwritten text or handwritten mathematical equations, and for deciding when the rice is ready. In all of these application domains, a trained human makes decisions based on sensory inputs and determines an outcome. As of 2020, such cases that require an order of half a second to a few seconds of human information processing can often be replaced or enhanced by deep learning systems. It is true that other statistical and machine learning techniques for y equals f theta of x may also do the job instead of deep learning. However, experience of the past decade has shown that with ample training data and multiple features, deep learning methods work exceptionally well, and in many cases surpass the performance of other machine learning methods, such as support vector machines, random forests, or other methods. Who are the personas involved? Due to its success, deep learning has been dubbed the new electricity. If that is the case, then who are the new electricians? The answer to this question is still evolving because the age of deep learning has just begun. Nevertheless, we can try and answer this question based on where deep learning stands as of 2022. As a first go, you may use general labels such as data scientists, statisticians, computer scientists, and machine learning engineers. People that train deep learning models would probably classify themselves as one of these. If their work involves using modeling to make predictions, gain business insight from data, or help finding scientific relationships between variables, then the data scientist label is probably the most appropriate. Further, if they use more statistical rigor for model selection and making conclusions, then a statistician is probably the right persona classification to use. This is especially true when the work of individuals involves experimental design and analysis of experimental data. Finally, if the work involves training and integrating deep learning solutions in software, then a machine learning engineer is probably the correct label. In terms of research and core development of ideas, many of the developers of deep learning ideas and technology are probably rightly called computer scientists. Computer science is obviously a broad field which at one extreme deals with the discrete mathematical theoretical questions, such as P equals NP or not. And at the other extreme includes ideas from artificial intelligence pioneers such as Frank Rosenblatt, the initial creator of the perceptron in the 1950s, and many others that worked on neural networks during the second half of the 20th century. In recent years, computer scientists responsible for the deep learning revolution include names such as Yann LeCun, Yoshia Bengio, Geoffrey Hinton, and many others. Other important names related to both the development of ideas, development of software, and education include Ian Goodfellow, Jeremy Howard, and Andrew Ng. These individuals, together with thousands of others, are responsible for recent advances in education of deep learning that made it what it is today. Most of these researchers would probably feel comfortable with the title computer scientists. However, you would also find mathematicians, statisticians, and neuroscientists heavily involved. Just a footnote. In general, this book aims to minimize historical notes, yet you may find more historical information in the notes and references at the end of this chapter and every chapter. In addition to some of the deep learning pioneers mentioned above, many researchers from other domains are also now focusing heavily on deep learning. This involves experts from the world of pure mathematics, probability, statistics, information theory, and control theory. In the years to come, we may witness development of theoretical results that describe deep learning, what works, what does not, and why. The focus of this book is not on such theoretical results. Our focus is rather on mathematical engineering, a phrase that we define in section 1.5 below. Okay, thanks for following our first section of the book, and go ahead and head on and listen to the video of the second section. If you found this video interesting, let us know what you liked, what you didn't like, and happy for any type of feedback. Thank you.